Hello everyone and welcome back to Introduction to Number Theory. In this video we will consider something like an explicit proof of existence of the solution of a system of congruences. This is about Chinese remainders theorem, and here we see a system of congruences with pairwise mutually prime moduli M1, M2 and so on, Mk. They're pairwise mutually prime. And we know that we wish to prove that for any set of right-hand sides, A1, A2, and so on, AK, well, for any A's, there will be a solution of such a system of congruences. Well, if we want to prove something as general as this statement, then why don't we start from more particular cases? For instance, well, consider a system of congruences. Well, denoted the unknown will be denoted not x but say y, and say that y is congruent to 1 modular m1 and y1 is congruent to 0 modular m2 and so on. Y1 is congruent to 0 modular mk. You may have noticed that I've denoted it not just y but y1. Well, because m1 is some kind of a special modulus for y1, because y1 is congruent to 0 modular all of m's instead besides m1, and it's congruent to 1 modular m1. And also we can consider a system of congruences where y2 is congruent to 0 modular m1 and y2 is congruent to 1 modular m2 and y2 is congruent to 0 modular m3 and 0 and 0 and so on, and finally y2 is congruent to 0 modular mk. And we can consider such systems of congruences for any modulus m. And well, let's try to prove that there exists such y1 with such a set of conditions. First of all, notice that y1 should be divisible by m2, m3, and so on, mk. So since m2 and so on, mk are pairwise mutually prime, then y1 must be divisible by their product. Let's write this product down, m2, m3, and so on, mk. So this is something y1 must be divisible by. And we understand that this product is mutually prime with m1. And as we know, any integer mutually prime with another integer is invertible modular this integer. Well, recall Euler's function, Euler's theorem, and so on. And this means that there exists an integer denoted as 1 such that the product of this big number here and S1 is congruent to 1 modular M1. And this means that we have Y1, all this we can take to be Y1. And similarly, y2 will be equal to m1 multiplied by m3 multiplied by and so on mk. This is the product of all m's except for m2, and multiplied by s2, where s2 is such an integer that this product is congruent to 1 modulo m2, and so on. So we can find y's for every modulus m1 from m1 to mk. Then, since we have solved systems of congruences of this type, we can write a formula for x. We can take x to be equal to a1 multiplied by y1 plus a2 multiplied by y2 plus and so on, ak multiplied by yk. And this x, this integer, will satisfy the initial system of congruences. Why is this so? Well, obviously, if we consider modulo m1, then all these y's are divisible by m1. Divisible, 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 all of these are divisible by m1. So all that is left is the first summand, and in the first summand we have a1 and y1, which is congruent to 1 modulo m1. Therefore, x is congruent to a1 modulo m1, and similarly, x will be congruent to a2 modulo m2, and so on. So x is indeed a solution. And this finishes the proof of existence of the solution. You may have noticed that these y's, y1, y2, and so on, are something like a basis in the space of the solution. Well, it is indeed so.